Hello and welcome to this week's presentation on arrays and lists. To start out, we'll talk a little bit about compilers. I assume from previous programming courses that you've used some type of compiler or development environment. Here in C++, because it's a cross-platform language, there's lots of different compilers to choose from. Some are free, some are command line, some have graphical interface environments or integrated development environments, they call them IDEs. Some examples are GCC and CodeBlocks. Intel has its own. There's one called Qt, and there are lots of others. Here at the classes at DeVry, we like to use what we call Visual Studio or Visual C++ for Microsoft. And you have a couple of choices where you can get it. One is you can get it through our virtual lab or iLab. You've probably used that before. Another option is that you can actually download a free version from Microsoft, what they call these days, they call it the community editions. You do have to register, but it's nothing. You just fill out a registration with an email, and you can have the community editions for free for as long as you want. So this is what I use, and you can have it locally, which is nice. You don't have to worry about connecting to an iLab. You can run it locally. Just to review, to create programs, we'll be creating what we call C++ console applications. So if you go to the menu and select File, New Project, and Visual C++, and Console Application, these are the types of programs that we'll be creating in this class. And basically it just gives you a command line window to work with. Some of the settings that you may want, obviously we want a console application, and it's nice to choose an empty project. If you don't choose an empty project, Microsoft will create some files in the project for you that you really don't need and can cause some confusion. So my preference is to create an empty project. Some of you may have taken previous programming courses in other languages, and if so, you may not have seen C++'s header versus implementation files. So I'll take a minute to go over that. In C++, a module is made up of, a code module is made up of at least two different files. One we call a header file with usually a .h extension, and the other we call an implementation file, which usually has a .cpp extension. In the Visual Studio editor environment, if you right-click after you've made the project, if you look in the Solution Explorer window here, so here's the Solution Explorer window here. If you right-click in the header file section, you can select Add and a new item, and that'll bring up a kind of a browser window where you can choose a location and select a file name. So usually we use some type of file name with a .h extension, and we put it in the project folder or some common source code folder within the project folder. Here I've made one called array.h. It gets opened up in the editor, and I can start editing the code in this file. In this example, I'm creating a dynamic array, and there's a couple of features in the header files that we may want to look at. Notice on the first line I put a comment. That's nice to have the name of the file. If it gets printed out, you know what the name of the file is. You may also want to put your name, some other comments about what this file is for. The next thing is these conditional compilation directives here and also at the bottom. What these are for, these conditional compilation directives, are to prevent the compiler from seeing the definition of this array class more than once. So if the compiler sees a definition for a function or a variable or a class, if it sees it more than once, it'll throw an error saying duplicate definition. So if this array class were included in more than one .cpp file, there is a potential for that duplication, that duplicate definition error to come up. There's a couple of different ways of preventing that. One is you may have used a pragma directive in previous classes. This is the way I prefer to do it with this conditional compilation directive. Basically this says is if not defined. So if this array underscore h token is not defined, then define it. And then down here to the endf. So this will ensure that this particular code will only be presented to the compiler once. And the name of the token array underscore h, I just use the name of the file and replace the periods with an underscore. Just something to make a unique token name or unique identifier name. In a header file, the important parts of the header file, we usually put class declarations and function prototypes. So here I'm declaring a class for a dynamic array I call CArray. It has 3 private data members. One is a pointer to an integer, so this will be a pointer to the actual data. One is the size of the array, how many values are in the array, how much of the array is being used right now. The other is the capacity, so we may allocate room for 1,000 integers in this case, but currently we may only be using 10 of those. Here's a private function to increase the capacity of the array, so if the user needs more than 1,000 things, we can increase the capacity. And then here's some standard public methods. One is the constructor, one is the destructor, print out the elements of the array, and then add a new value into the array. And notice that these are just prototypes. There's no actual code here. These are just definitions of variables and prototypes of functions. The actual definitions of those functions will go in the implementation file or the .cpp file. So to create an implementation or .cpp file, we use a real similar technique where we go to the Solution Explorer and we right-click on the Source Files section and we select Add and a new item. And here I'm creating the implementation file for the array module, so I call it array.cpp. So notice the modules generally have the same prefix on the file name and differ by the suffix .h or .cpp. Once I've done this, I'll have a array.cpp file in the editor window, and I can start adding the function definitions there. So these are the function definitions here. Notice at the top of the file I include array.h, so the compiler needs to know what a CArray is. It's a class, but the compiler won't know it unless we include this array.h. Also, if I want to be able to print using cout, I'm going to include IOStream and say that we're going to use the standard namespace out of the IOStream library. Here's the constructor, and in this default constructor, all that's done here is set the data pointer to a null pointer and set the size and capacity to 0. In the destructor, we ask if the data pointer is not null, and if that's true, if the data pointer is not null, which means it's pointing to something, then we deallocate that data, set the data pointer to null, and set the size and capacity to 0. Print, fairly straightforward. We just use a loop from 0 to the size of the list, and then print out pdata sub I. We just treat it as an array. To add a variable to the list, we first check to see if the list is full. So if the size is equal to the capacity, then that means that the list is full and we want to increase the capacity. And in this case, every time I increase the capacity, I increase it by 256 integers. And there's different policies that you can implement. You may want to double it each time. You may want to use some other strategy for increasing the size of it. In this case, it's just increased by a constant size whenever an increase is necessary. We take the new value, we put it at the right location, which happens to be size. So this is an interesting use of the size data member. Not only does it store how many items are currently in the list, but it's also the location of where the next thing should go in the list. It's kind of an interesting use of that. And of course, after we've added the new value, then we just increase the size by 1. If we need to call this increased capacity, here's the definition for it. And in order to increase the capacity of a dynamic array, we actually need to make a second copy of this. So we can't delete the old array, we can't delete the original array without losing the values. So what we do is we make a copy of it in a temporary pointer, and then we create a new array that has the new capacity, the new size, and then loop through the size and copy the data from the temporary into the current list, or the new sized list, and then we delete the copy of the old one. And I just realized it looks like there's a bug here where this new capacity is always going to be 256. And so what we should have done here in this code is set the capacity variable. So right in here at the top, we should have set the capacity variable to be equal to the original value of the capacity plus new capacity. So we should have said capacity plus equals new capacity, and then used the capacity in here as the new size. So it looks like we've got a slight bug here in the code. Also notice that there's not as many comments in here. We could definitely use more comments on this code. But the basic idea on this implementation file is that we provide definitions for the prototypes that were in the header file. So the next step in getting our overall program to run is to create an additional implementation file that will have the main function. This isn't necessary. We could have done it in the array.cpp file, but in a large project it's often broken up this way, where you have a separate implementation or CPP file for the main function. And in the code for this, we include the array header file, we include IOStream if we need to use cout or print out anything. And notice in main I create 2 instances of our dynamic array, our C array, and in the odd list I add in or insert 1, 3, 5, and 7, and in the even list we add in or insert 2, 4, 6, and 8, and we print them out. Pretty straightforward use of these lists. To build it, we go to the build menu and select build solution, and depending on the arrangement of your user interface, you may or may not see an output window. If you go to the view menu, if you go to the view menu here, I think you'll find a link to the output window. And here in the output window, after you've done a build, you'll either see a success message, or you may see some warnings and or error messages. If you get error messages, you'll need to fix those before you can run the program. To run the program, we go to the debug menu, and we can choose start without debugging, or if you want to use the debugger, you can do start with debugging. Here I use start without debugging, and then you can see the output generated here as we expect. In C++, there's several different choices for arrays or storing lists of information. We're all familiar with the original basic array and the pros and cons. Some of the limitations is that a simple array is homogeneous, which means that every item in the list has to be the same data type. One advantage of a basic array is that all the elements are contiguous in memory, or they're adjacent in memory, and this makes processing basic arrays very fast because they're right next to each other in memory. Another downside or limitation is that the size of these basic arrays are fixed at compile time, so it doesn't allow for any flexibility in the size. The dynamic arrays that we saw in today's example code does allow the size to change. However, a resize requires that we make a copy of the old values in the old size list into the new size list. So every time you resize the list, you have to make a copy. Imagine if you had a list of thousands of things and you kept adding new things one at a time. That list would have to be resized and copied fairly regular, depending on what your strategy or policy is on increasing the size of the list. Also, using pointers like this brings up the potential for what we call memory leaks. So for example, if you have a bug in your code that resizes the list or increases the capacity of the list such that the memory is not freed up properly, then this can be the source of what we call a memory leak, and that can be a potential problem. There's also a linked list implementation where adding and removing items from the list is very fast, but the items in the list are not adjacent in memory, or not necessarily adjacent in memory, and so walking through the list or processing the elements of the list in order may not be quite as fast. We'll take a look at that implementation a little bit later in this course. And also within C++, they've come up with this thing called STL, or the Standard Template Library, and it is a library of a variety of different types of containers, including dynamic array and linked list and stacks and queues and sets and so on. Here you can see some documentation from one of my favorite websites. This is called cplus.com, and it has a lot of good documentation on the C++ language, as well as tutorials and a forum and so on. Not sure how well you can read this, but some of the containers in here are array, queue, set, map, vector. So there's a lot of good, useful containers. Each of them have their own pros and cons. And as a developer, one of our tasks is to choose the appropriate container for our particular application. Here's just an example of a vector. The STL standard template libraries, they do use templates so that the vector then can be of whatever particular data type you like, including your own custom data type. So you could have a vector of C array if you wanted to. Here I've got a vector of integer, and the vector is called mylist, and then I say mylist.pushback2, so now 2 has been pushed into or added into mylist. Unfortunately, the names of some of the methods are not quite as intuitive, so instead of add or insert, they use names like pushback, and some of the other names may not be quite as intuitive as you might expect. But the nice thing is that the standard template library is available in just about all implementations of C++, so you should be able to find it in almost any environment where you program C++. When we use the standard template library containers, especially lists, it's very common that we want to traverse the list or to loop through the list. Here I'm going to show you a few examples of how to do this. And all these loops do the same thing, but they use slightly different syntax and slightly different ways of doing it. The first technique here uses just standard indexing. So we have an index-based loop where I goes from 0 to the size of the list, and then we print out my list sub I. And notice how my list is a vector of integer, and we've got 4 even integers, 2, 4, 6, 8 in the list. The next more generic way is using something called an iterator. And the reason we have iterators is that some container implementations are such that the elements in the container are not contiguous in memory, so they're connected using pointers, which means you can't index them. You can't say this container object sub 0 or this container object sub 3 like you could an array. So you have to, it's more convenient to use something called an iterator, or more general case to use something called an iterator. Unfortunately, the syntax for iterators can be a little bit odd. Notice the data type for this iterator is vector of integer type : iterator. So that's kind of an odd syntax for the data type. And in this particular loop, we set the iterator to the beginning of the list, my list begin. We continue to walk or traverse the list until the iterator is equal to the end of the list. So as long as the iterator is not at the end of the list, we keep going. And then to move the iterator to the next position in the list, we say ++it. So the increment operator here has been overloaded on this iterator object. Here we print out the value of the iterator by dereferencing the iterator. So the iterator is not really a pointer, but the dereference operator has been overloaded to get us access to the value at that particular location in the list. So this is the more generic way to traverse a container using iterators. One nice thing that's happened with the C++ 11 standard is that they've come up with this auto keyword. So we can do the same, have the same code here, but not have to worry too much about the data type. The auto keyword will infer the data type for the iterator based on what the return type of the right-hand side of that equal sign is. So it will look at that function signature and say, oh, this returns a vector int iterator, and it'll use that as the data type. So that's kind of nice. This final version here uses a new feature in C++ 11 called a range-based for loop, and it also uses the auto keyword. So this is similar to a for each loop that you may have seen in other programming languages. We say for auto reference val. So this val then is a reference to the data type that's inferred from this list, in which case that data type is an integer. So val then is a reference to an integer. In the first iteration of this loop, val will be a reference to the first value in the list. The second iteration, it'll be a reference to the second value of the list, and so on. So what this does is it essentially lets val take on the values sequentially of each element in the list, and then of course we just print it out. Notice that because it's a reference to the value in the list, if we were to do something inside the loop like say val equal 3 or val plus plus, it would actually change the values in the list. And that's because we used the reference notation here. So we covered a lot on the compiler and different types of lists and arrays and a little bit of the standard template library. I hope this helps you with your assignment this week, and let me know if you have any questions.